Okay, so in this last couple of minutes, I'm just going to show that how having a pre-sorted array can sometimes help us to solve other problems. Okay, of course, we have already seen an example using binary search to do search queries, having a sorted array, making search queries much more efficient. Okay, but here's another example. So remember that earlier we mentioned the movie problem, where you're in a flight, you're given a list of movies where you know their lengths, okay? And the flight duration is D, and you want to find 2 movies whose total length is exactly D. Otherwise, you return none because you don't want to waste any time, but you also don't want to not being able to finish a movie, okay? Now, remember that previously we're given an algorithm which just check all possible combinations. You have n movie, check all possible combination, give you and choose 2 choices, and then each one take constant time. That's why you take a time complexity n squared, because they just brute force check all possible combinations, see which one the total length, whether any pair give you total length D or not. Okay, and the question is that can we do better? Okay, and it turned out yes, we can, and especially if we first sort the input array of the movie times, the length of the movies. Okay, so how does the sorting help? Okay, so here's an idea. Okay, let's say that your flight time is 170. Okay, so this is D. And you're given a list of movie times which already sorted. Okay, so we first do a sorting. Okay, and how do I figure out whether any 2 add up to 170 or not? Okay, well, imagine the following. Imagine that first, I'm going to use a pointer here and then use another pointer here. So this is smallest and the largest. Okay, I'm going to first check the sum of these 2. So 60 plus 130 equal to 190. All right, this is bigger than my target time, which is 170. Okay, from this, the question is, what can I induce? What can I deduce from this? Well, I know that this 2, right now, this is smallest, okay? And 130 plus the smallest possible number still give me a number which is bigger than my target number, okay? What does it mean? That means that 130 cannot be one of the movie which give me 170. So you're looking for, so your goal is to find the movie 1 plus movie 2, whose total time is 170, right? And 130 cannot be that movie. Why? Because even if you use the smallest movie time, the time is still, total time is still too large, okay? And if you pair this movie with any other movie, the total sum of lengths of the time can only be larger. So it's not possible to be one of the my candidate movie. So I can rule this movie out. So I can safely throw 130 out. I don't need to compare this with anybody else anymore. Okay, what does that mean? That means that now I can move my pointer. So 130 is out. Now I move this pointer. I can move it to 110. Okay, next I compute 60 plus 110. This time I exactly got 170. That means that we found 2 movies which give us time 70, whose total time is 170. Then we return. That's it. Okay. Maybe go with another example. Instead of 170, let's say that my target. Let's say that my target is 175. Let's see what is the algorithm to do that using this similar idea. Okay. Well, at the beginning, I first going to check between the small and the largest. Okay, so I do 60 plus 130, that's 190, which is bigger than 175. This means that 130 is ruled out. It's not possible to have this movie to give me total time 175. Okay, so now I can move this pointer here. Next, I do 60 plus 110. This is 170, and this is smaller than 175. What does this mean now? Well, this is basically the biggest movie time possible, because 130 is already rolled out, okay? But 60 plus the biggest possible is still not enough. It's still too short, the total movie time, okay? That means that now we can rule out 60. It's not possible to have 60 to give me some two movie to pair up with another movie whose total time is 175, okay? Because it's going to be too small. So this means that now 60 is ruled out. That means I can move the pointer here, okay? I continue, now 80 plus 110, that's 190. And this is too large. Again, by the same token, one is too large, that means this one is ruled out. Then I get 80 plus 95. And this time, we happen to find it, we're done. If this last two, if this is not 95, but 94, so last two still didn't give me the correct time, that means I couldn't find it. Then I should return none. So that's the idea. Okay, so that's, and you can see this is where the sorted structure help us. Why? Because at any moment, I know, for example, 130 plus 60, when it's too big, I know I can throw out 130 because I already know 60 is the smallest possible movie that I can choose. Okay, so I'm using the sorted structure here. All right. All right. But how do we realize this idea using an algorithm? Well, here's what we have. So remember the first step now, however, we have to first do a sorting to sort this array, because for this previous idea to work, we need to have all the movie times first sorted. Okay, so we first sort all the movie time. Then we have the two pointer. One is the shortest one, and one is the longest one among the possible pair of movies that you can that will give you the total time D. Okay. Then what we do is at any moment we test what is the total time of the current two movies pointed by these two pointers. Okay. If it's equal to the target D, we're done. We found it. So this is a two movie. We return the two movie ID, okay? But if it's smaller than the target, what does it mean? It means the current smallest one is too small, because even when I added, when this movie is paired with the largest possible, the movie with the largest length time, is still not enough, okay? That means this one can be ruled out. So we ruled it out, and meanwhile, we increment the shortest index by 1. Okay, and then the same for the otherwise, the longest one. That's it. Okay, so what's the time complexity of the algorithm? Well, this step we have to first do sorting, and we just said merge sort. If we use merge sort, it takes n log n. And the remainder of the algorithm, we have a for loop with n iterations. And each iteration only takes constant time. So the total time complexity as such is n log n plus linear, which is still dominated by n log n. So that's the time complexity of this algorithm. So again, compared to what we had before, which naively to solve the movie problem, we need to do it in n squared time. But now, by first sorting it, we can actually solve it. So after sorting, only take a linear time, but we have to also add the cost of sorting itself, which is n log n. Okay, so this is to make the point that the using sorted structure, you basically make this input has more structure now, can sometimes help us to solve other problem more efficiently, may not even be obvious at the beginning. Okay, both the binary search and movie problem of this. Okay, another important take-home message of this lecture is that sorting can be done in n log n asymptotic time, using the merge sort idea, and this is actually the optimal. So this is the best sorting algorithm, asymptotic time speaking, that you can have. Okay. All right. So that's all that I want to talk about today.